Hey guys, good afternoon. So in the previous few talks from Amrit and others, you actually looked at applications that used ready-made ML toolkits within different applications, yeah? What I'm going to do is, as part of some of my work, we've had to work with core ML, not just using libraries, but actually working with the algorithms, trying to figure out what's best, how machine learning actually works. And during that process, I realized that figuring out ML was different from programming that done until now, right? So it would usually be the case that, I understand Java, I understand C#, I understand Go, and over this weekend, I'm going to pick up machine learning. And that has not been my experience. And I struggled with the initial part, and I remember some of the questions that I asked on Stack Overflow and all, they seem so stupid right now, because I did not have that initial help in trying to figure out what exactly is ML, right? What's the approach to it? It's not a programming approach, it's a different approach. So in these three sections that I have, in the first part, I'm just going to do to figure out what and why is ML. How does it exist? How does it solve problems? In the second part, we'll do a little bit of deep dive, but not so much. And third part, if I get enough time to cover it properly, then we'll look at how Google kind of creates using the things that we learned in section 1 and section 2, how they provide ready-made APIs that you can plug and play into, right? Which is what a lot of the other talks have been. So about me, today I have invested in quite a handful of companies. Just so happens that 3 or 4 of them happen to be in the artificial intelligence and machine learning space. And I continue to be a technologist. I continue to advise them. Every once in a while, I write their back-end, front-end, try to figure out the algorithms for them. So I'm still very much involved in the technology part, even though I'm financially helping them also. And I'm trying to build that expertise up. And one part of the slides that we'll see right now is that even if I don't care to cover the whole thing, I intend to do more sessions along with the Google Developer Group or the Google Cloud Developer Community to do more breakout sessions where we can do weekend hands-on training and workshops so that you can be competent enough and do your own startups or work in your own companies that could have data science as a requirement. So today I mentor a bunch of technical teams, a couple of startups or accelerators. I work with them when they call me, mostly to advise and to kind of give them directions on what to do, whether it's Kubernetes or whether it's what technology backend to adopt, kind of help with that. Yeah. And so I continue to do trainings, a little bit of developer evangelism. So to start with the why and what of ML, right? So traditional programs that we used to work on, this is how they work, right? You code in or you codify a set of rules into a system. You tell the computer, do this, do that, this step, that step, and that is a guarantee provided by the computer that irrespective of where you run it, if it was a cross-compiled program, different operating systems, the language it provides, the CPU provides, is a guarantee that will run the exact same way wherever you run it, right? So this guarantee is not always there in the case of machine learning. So in the original way, you codify the rules, you write code for it, and you give all these if conditions, or you write the business rules. Then you apply data to it, pass it through compute, and get your answers. So if you had, for example, a problem where you're just trying to figure out what is a straight line, you've got the equation, say, y is equal to mx plus c, where you're given the slope, you've gone get the intercept on the y-axis, and given different values of x, how do you compute y, right? That is the problem. So the rule over there is equal to mx plus c, and y is the answer. And you're able to apply that very fast, very quickly, and get a lot of results. The tough thing with some of these problems is that the way computers deal with problems, certain problems are very easy, right? So if somebody clicks a photo over here, it's easy to figure out where they are, right? You just tap into a geographic information system, find out the location with the latitude, longitude, and say, okay, this person is right now within the DevFest area. But then to figure out, let's say if that person has taken a photograph and say, who is this person in the photograph? Or what is even that is happening? That is a much tougher problem. So in this XKCD example, somebody's taken a photograph in a national park, and you're saying, they're trying to figure out where is it? Easy problem. Now the next thing is, can you figure out if the picture you've taken is a bird? And the developer replies, okay, the other one I can do in half an hour, but this one is going to take me an entire research team and about 5 years of work. So the complexity of these problems is so hard that sometimes it's difficult to codify them. Another simple example is if you had an image, right? It's easy for the computer to figure out what the pixels are. Give me the value of the RGB or the RGBA value at pixel 1.1. 1,1, it's easy to get that, right? The computer knows that very quickly. But to figure out what is the image, that is a much, much harder problem. And codifying it is not easy, right? To write code for it. So even in this particular thing, you can see that there are 3 animals there, fairly similar, all of them are cat family probably. The first one is a domestic cat, the last one is a little baby tiger. But what's this middle one? Even we kind of find it difficult, right? It's probably a bobcat or a lynx, and we don't know exactly what it is. It's difficult to, even for us to guess it. But for the computer, it's a much, much more complex problem. So there are 2 paths to finding answers. One is deduction, which is say, what are these things? Given this data, what does it represent? What is it? And there's a second part to it, which is induction, right? Given the data that we have, what can we predict? So if you're doing an autonomous driving system, it's not enough to find out whether, it's necessary, of course, to find out whether there are pedestrians over there, or it's a lamppost, or it's a mailbox. That's important to find out. But it's also necessary to kind of predict what they're going to do. Are they going to move in your direction? Are they moving the other direction? So in this image, the man is walking away from the car, while the lady is walking towards the car. That's very important that you find that out. And it's very difficult to, again, code that in. So part of the requirement is not only to find out what happened, but also to kind of predict the future. And one thing when you predict the future is, you don't always have absoluteness, right? You have a probability. You say, it might happen. And the question is to get, or the answer, or the closest you can get to the answer is to get to a probability closest to 1, and not necessarily get an absolute answer, which is what we are used to in traditional programming, right? You don't get random numbers every time you run a program. There is a consistency to it. So existing systems, they tend to be expert systems. They are rule-based. You code in a bunch of rules and say, how do you work on, how do you get these answers? So if you were to say pick up, or if you write a program that just to pick up eggs, you might think it's a simple problem, but then you start with 1 egg and you realize, okay, this egg has got this, it's got about 2.5 centimeters this way, about 2 centimeters that way, and when you try to pick it up, apply so much amount of pressure or force. And now when you come to the next egg, you go from a chicken egg to, say, an ostrich egg. Now you've got a completely different problem, right? And you need to code that in right now. So you need to add the business rules. You need to find people who actually understand eggs and ask them to kind of figure out what is the size, what is the weight, and see how much pressure to apply to it. And now we're just talking about just 2 kinds of eggs, and we've already got so many rules in place. So what happens when we pick up, say, all kinds of eggs, say, all other bird eggs or reptile eggs or fish eggs, which is a completely different, data for each of them. And then we're talking just about eggs. But what about books or chairs, or if you have to pick up Thor's hammer? What is the rules? What are the rules required to code this in? Okay, big complex problem. So one inspiration to how we can solve machine learning problems is not to look at codifying it, but to kind of figure out, how do babies learn to identify things in the environment? So it is not that as soon as they're born, the doctor, says, here's a book, read up all the rules over here and try to figure out which is an apple, right? You don't get nobody's giving them a whole set of rules to say, this is how we figure out what's an apple. If it's red and round, probably an apple. If it's yellow and round, probably a tennis ball. It doesn't go like that. There is a different approach to it. So what is that approach? Typically, these kids, they're given repeated impressions of a particular kind of data, right? You take an apple and say, you tell the kid, apple. And you show it a tennis ball and say ball. You show it an orange, say orange. Or you show it its daddy and say dada. Whatever it is over and over again, you kind of impress upon the kid that this is such an object, right? So you're giving it what? You're giving it data, and then you're giving it a label. You're labeling the data that you've given it and saying, this is what this object is, right? So instead of the human learning approach being codified, it is based on repeated impressions where it kind of figures out what is right and what is not, right? So even in doing that, you also need to give it negative examples, not just positive examples. If it points to an orange and says apple, you say, no, that's not an apple. That's an orange, right? So you give it positive examples, negative examples, and get the kid to kind of recognize objects in its universe. It is also the same with coming up with answers, right? Now we're talking about labeling. There's also the thing about if you ask a question, what is 5 into 5? And if it says 3 million, then like, no, it's not 3 million. 5 into 5 is 25. And you kind of explain the idea that you've come up with the wrong answer, and you need to correct that number, right? So the approach to machine learning then is to go from data plus answers or data plus labels onto rules. So you give it data and get the system to figure out its own rules, which seems to work very well for a certain class of problems, especially that involves large amounts of data, labeling, and predicting. So many years ago, I think about 5 or 6 years ago, I was at a hackathon where independently, I didn't know about machine learning and all at that point. I was like, you know what, is there a way to derive information from data? So I didn't win this particular hackathon, but I did this thing called data viz, where given data, I wanted to figure out what are its constituent information that I can use, right? So over the period of that 1 or 2 days, I created something where given the data, it is able to figure out that what are reasonable charts or graphs that you can draw from this. It was not much of a project. I didn't win that hackathon, but the idea was there that how do you get these things to be independent, right? Discover itself. How do you get systems to discover itself and then do something? I didn't know about ML. I didn't do a good job of this, but at least I got the idea that, you know, that's an important thing that could be done. So I went back. I was also thinking about how to automatically figure out regular expressions. Given a bunch of strings, is it possible to figure out what is a regular expression that matches that? And I tried that for quite a bit, and I just couldn't get it because the amount of data that is involved and the number of combinations that are involved are so large that it's difficult to find a good regex match for all the inputs. So the goal of machine learning then becomes to discover meaningful information from data, right? Instead of codifying it, you look at the data and then figure out what is the information, as opposed to bringing an expert who will codify the rules for you. The typical approach then is to collect a large amount of data from the universe, or from the, when I say universe, the universe of stuff that you're dealing with, pass it through some kind of system so that it tries to come up with the parameters that will identify or connect the answers to the data that comes in. And that thing is called a model. Then you can try to infer from that. You apply new data to that model, and once you do that, you kind of check, is this as expected? I was expecting a value that this comes out as orange, but it actually came out of apple. Now I see there's a difference between them, and I go and correct my system. I correct my model to then create a new model that will be a little more refined than the last time that I did it, to get a system or a prediction mechanism or a model that predicts more correctly, right? There's no absolute correctness in this, but with each iteration, we want to get better and better and better. So the approach to creating models is to collect a large number of data points. So one of the examples is, say, for example, if you're trying to figure out how the universe, the general universe with all the heavenly bodies, how that works, you collect a large amount of data which there is, like, for example, the movement of the heavenly bodies, the stars, suns, and then kind of see how will that work. Yeah? Now, there are some models that are bad. So there was one cleric that actually said that whenever earthquakes happen, the reason is because women wear jeans. Which, if you look at it, is kind of correct, right? Because every time there has been an earthquake in the recent past, there has been some woman who's worn jeans. So it seems like, okay, there is a correlation between the two things. But clearly, you know that that can't work, because millions of years ago, there were earthquakes too, and it was not like, dinosaurs were walking around in jeans. So there's no connection, right? There's no causation from one to the other to say that if women wear jeans, then there's earthquakes. So you can start off with any hypothesis that you want, but it has to fit all the data that you've created. Yeah? Another thing in the idea of figuring out the movement of heavenly bodies is the Flat Earth Society. I don't know if you've heard about this, but a bunch of people in the world, and not a small number, who actually believe that the Earth is flat. Right? And there's no amount of data that you can show them to convince them otherwise. So again, you've got all this data saying there's all the motions of the movement of the planets, but they come and say, you know what, that doesn't matter, the Earth is flat. And there's not even a joke, yeah? There are a bunch of people who absolutely believe this. Another approach, another model would be a geocentric view, where the Earth is at the center and the stars and the heavenly bodies are rotating around it. But there's a problem with this, okay? In certain observations, you see that they're not actually moving in a circle or a semicircle. They do something called retrograde motion, right? So in having a circle model, you're unable to fit that data into that system. So long back, there was another person called Ptolemy who was in the Pythagorean school of thought, right? And they had to have these perfect shapes, and their favorite shape was a circle. And everything they tried to fit in, all the motion of the heavenly bodies, they tried to fit in a circle. And to fit in the, this retrograde motion, where it actually spins around, or curves around and comes back, he put circles within circles, and what are called epicycles, yeah? And made a very complex model that kind of said what is the movement of the heavenly bodies in the universe. Now, this is a model that worked partially, but didn't work very well. The other big problem was that this was a very complex model. As a complex model, it becomes difficult to kind of work. And most models, if you see, they don't tend to be extremely complex. They seem to be fairly simple. So eventually, there was the heliocentric model, which was the sun at the center and the orbits being elliptical, which was now, if you see, a model that not only fits all data, but is also a simple model. Okay? It's not overly complex. You're able to predict stuff. You're able to describe or deduct why certain things happen, and also induct and say what is going to happen. You can predict hundreds of years from now when there's going to be a solar eclipse. Right? So this is a good model and a realistic model. So the two things to the prediction correctness of a model: one, it has to fit existing data, but not overfit. An overfitting model would be kind of what Ptolemy did, to say it becomes a complex thing and works under specific circumstances, but if you give some other data nearby, it gives a completely different result. Okay, that's not wanted. And of course, it has to make reasonably correct predictions. So the next set is to say, how do we approach this? So in the beginning, when I tried to figure out some of these things, I was trying to code machine learning, my question was, how do I actually code it? Like, I was exploring, what function do I call to get one particular result? And that's not the way it works. So the approach to it is that you start off with a bunch of data. And this data, let's say for simplicity's sake, we've got it on a 2D plane. And we've got all these scatter points. And the idea is that we want to draw a reasonably smooth curve through these data points that connects them kind of well. Remember, again, when you see this data, the data points are not all on the line. Right? You want to make reasonable predictions. It is not that they have to be exact. For example, let's say you want to predict what is how many people are going to be riding the metro today in the Bangalore metro. You don't want an exact number saying 25,322 and maybe one kid. That's not what you want. You want to say it's around 25,000, around 23,000, right? So you're trying to make predictions with a fair amount of probability as opposed to trying to be absolute. Right? And even within this, there's something called precision and recall that we'll come to later. The curves themselves we talk about typically in 2D plane. They can be a straight line that you see, it's again 2D plane, or a curved line within that thing. And you will have different orders. If you're trying to fit an equation, one line, the first line will be y equal to mx plus c, but the other one will have multiple orders. There'll be x squared plus y squared or some variation of that. You can also have another kind of thing. So that's called regression. The first, the top left two are regression. The second one, that's not an accurate diagram, is something called classification. We are trying to group items together. Right? Say, let's do doing a movie recommendation. What are the kind of movies that you like? Will you like action or drama? Right? Those are two different sets of groups. And remember again that these, typically with the number of parameters you have, the weights that you have to connect these different points, you will have it at multiple dimensions. So we, as humans, are unable to think beyond the third dimension. But remember that some of these models are actually working in dimensions that are hundreds of thousands order, right? Or millions, actually. It is not unnatural to find complex models that work in dimensions in, say, hundreds of thousands or millions. But you don't have to really draw it out, right? If you get the idea that at a 2D level or a 3D level, this is how it works, you can just use a computer and all its array computations and all to do that for you instead of you having to understand every little detail. Sorry. So what is the process of machine learning then? The process of machine learning now becomes, given a curve, right, or given data, how do you fit a curve to suit that set of data? Okay? So in the diagram that you see, we actually have a system of, it's just a graph, illustration. We have a system of pulleys and levers that can be moved, whose weight can be adjusted, so that you get a particular curve, right? So we expect that as when new data come in, you move the pulleys around, right? You change the weights on these pulleys until you're able to map out the flow of data in that diagram. So if the diagram had a curve, you want to be able to move these pulleys and adjust these weights until you get a bunch of weights that gets very close to the points depicted on that graph. Okay? So this is one of the key parts. There was another very interesting blog I read recently where they talk about what is actually happening inside the model, and I didn't understand it, but I'll just tell you if you want to look it up, is instead of trying to plot these curve graphs, what these models are internally doing, okay, is that it's actually trying to create straight lines or straight planes across multiple dimensions by curving space. Okay? So we look at space as constant and we curve the line, but actually what is happening inside the model is it is actually keeping the plane or the line straight, and it is curving the data plane that is working on, or that universe is being curved, or universe of data is being curved to fit these lines on a straight or a horizontal plane. Very interesting thing, but I honestly didn't understand it that much. Inside these, some of the deep learning models, these weights that you figured, that you want to figure out actually happen at multiple levels. So deep learning network is one where in the colored lines that you see between the circle and the inputs at each point, each of the circles become neurons, and the lines connecting them, they are weights. Yeah? So if you were right now taking an image, say an 8 megapixel image, let's say you've got about 8 million pixels in it, you will have 8 million input points for this particular model. 8 million input points. Now you connect that into yet another 8 million neurons. You've got 8 million into 8 million set of weights that you need to work with. Okay? So these are huge, high dimensional problems that needs, again, as you can see, they require a lot of computational power. So in our example that we can do, let's say we are trying to figure out whether somebody will like a certain kind of movie. Okay? So we've got Spider-Man, we've got Superman, and we've got Padman. Now, is a person who's already seen Spider-Man and Superman likely to go watch Padman? Right? Though it sounds very similar, are they in the same genre? And that's a recommendation system that we want to work on. So one of the companies that I'm investing in, they're doing this recommendation system where they're working with different data and saying, given all these things that the user has already done, what is the next thing that he'll probably like? Yeah? And they're not doing just for movies, they're doing it for a lot of different things. So in this, it's not enough to just give it a poster of Superman or Spider-Man and say, will the person like it? Instead, we need to kind of work with the data, piece it out, give different columns, and figure out what defines these particular movies, right? So there could be, for example, is there a heroic figure? Well, Superman, Spider-Man, and Padman, they're all heroic figures in some way. Yeah? Is it the genre of the movie? Is it action? The other one is drama. So by computing all these things, these are called features, you figure out the features in your model for the data that is coming in, apply this processing on it, and try to guess what would be predicted next. Okay? In connecting all this data, the features that come in, and the labels that exist, what you're building up is the model with these weights that I talked about, which, when given new input, will be able to give you a new label. So that is a process where you've got the features, somebody's labeled them as an expert, and then you're trying to do the next part. So the next thing is also to be having, we need to kind of not only run the model to kind of train it, but we also need to test it. Okay? And in that we'll split the data into what is called a training set and a test set. If you're doing something called cross-validation, where you want to run on the same data, you want to run it over and over again, you do something called cross-validation, where you have a training set, a validation set that you work with multiple times, and finally do a test. On the test set, if the idea is that you get a score very close to what you expect. So when given a label, if somebody's run Superman through it and you get a label that he's watched it and he's liked it, when you run the test, you want to get the same label. If you don't get the same label, then there's a difference. There's a difference between the predicted value and the expected value. You expect that this person is going to like it, same with the probability of, say, 90%, but you actually show 30%. Now we've got a loss, okay? A difference between the expected value and the actual value, and let's say that's about 60%. You need to now feed this back into the network, okay, to get the weights to adjust itself. So let me just go over that very quickly. You start with data, some input, you run it through your system so that it adjusts its weights to get an output. At the output side, you compare it with what you already had. And the difference between what you had and what you've predicted is called the loss. And this loss has to be back propagated into the network so that all the weights along the path that came is adjusted again, right? So there's a huge difference. You adjust the weights by a large amount. If it's very, very nearby, you adjust it by a small amount so that all of them are then updated, and you have an updated model that you will be closer to the right prediction. In the process, there could be something like overfitting and underfitting. We saw that with the Ptolemy examples, where he had overfitted the data, whereas a flat Earth person would have underfitted the data. Within this itself, there's something called parameters, the weights that are understood by the system, and hyperparameters that you will set. So you need to figure out what are the different functions or what is the model that you will use to do this. And how long should it run? How deep should the network be? These are all parameters that you set it. There's also a learning rate. How quickly should it converge to a point? Certain models will converge very quickly, whereas certain will take a long time. So these models, the amount of data, it could even run for months. And Google advises that if it runs for a month, you've got a bad model. Yeah? Go back and figure it out. But it's not unnatural to have one model creation process going for about a week. Okay? It's not unnatural, even with the large amount of CPUs and TPUs and all that you have today. As a part of this, the output will be, one of the outputs that you will get in your testing process is whether you get false negatives or false positives, right? So if you predict that something is an apple and actually is an apple, that is a true positive. If you predict something is not an apple and is not an apple, then it is a true negative. But the opposite can happen. And this is very important to figure out what you want from a model. There are some models where you don't want to make any mistakes. But for some models, it's okay to make some mistakes. Say, let's say you're screening for breast cancer, right? It's okay if we say somebody who's not got breast cancer, after the screening process, who got breast cancer, you actually probably have, right? So that you do additional tests. But you don't want to miss anybody who's actually got breast cancer. So there are certain values in terms of the precision and recall. This is called precision recall. Like how much of what you predicted is correct and how much of what you predicted is among all the predictions that you did. Different values that you need to consider with respect to precision and recall. So to work with machine learning, you can see now you need large amounts of data, large amounts of compute. Speed has to be very high for the kind of compute you're doing. And you must realize also that some of these things, like the other speakers said, they're happening at runtime, right? They're not all being done offline. While you're working, you need to be able to predict what's the next word that comes in. Or what is this, I mean, who is this person? Is it he's a young person, old person? Or the actual identification of this person is Mr. X and Y. So the whole process is a repeated process that you need to run over and over again, including data collection, model selection, feature engineering, training and tuning, and to figure out what is the error and to come back and do that over and over again. Huge amount of technical challenges involved, and some of the talks within Google have told that the actual time you spend doing machine learning, core machine learning, is actually 5% of the total project time, right? So where do you spend all the remaining time? It's what you do currently also with your with your deployments. You need to be able to deploy it, you need to be able to scale it, you need to have security, logging, monitoring. And me, in some of the work that I've done, I found the Google Cloud ML engine to be fairly good. Okay? And I'm using it for a lot of my demos. I'm trying to get trained on it. I'm training other people. I'm helping other people with their projects. And it's worked out good for me, and I think you guys should also try it. So how does Google do ML? They've got a large amount of tools. In just data analysis, it's amazing. Okay? There are 2 courses I'll recommend towards the end of the system that I've done both, and a few others also. Both of them have a very good view into how you actually do your own ML engines. Okay? The AI/ML tools itself, they have done a lot of the work for you so that you can plug in, right, into whether it's the TensorFlow part, that's a library that you'll have to code, but there are things that you can just directly call an API and get the results that you want, which in itself is amazing. So how does it do that? One interesting thing is called transfer learning. So if you had to study each of these things by yourself and do it, it takes a long time. So with one of the companies that we're working with, they were trying to do image recognition for over a month to find out or to figure out, to label certain kinds of images. And we went and looked at it and said, you know, we really don't need to do that. Just use the ML engine. We plugged into the Vision API, and within like an hour or 2, I had a demo that I could show them, and they were convinced enough to say, you know what, yeah, that's actually the path we should follow. So it's very convenient, but at the same time, there's certain things that you cannot get done by the Google Cloud Engine, which is why you need to still understand the whole modeling process, all the algorithms that are used. Not only for that, but also to pick up what model to use. Okay, there is a requirement at a certain level, but if you don't need that, plug into these APIs. So one thing is called transfer learning. Transfer learning is this approach, and this is part of the course that is given by Google on this, is the idea that given that you've done a lot of work, why do you want to do it all over again, right? Start halfway, take that piece, and reapply it to a different situation. Okay? So in the part of what machine learning is basically you're traveling through weight space or parameter space to find out there are all these different values, okay, on a plane, let's say, and you're traveling through different points to find the one that matches your particular data, right? So in doing that, why would you do that over and over again? Start from some point that you know is close to this final result that you want and just move there. Okay? So this is called transfer learning, where we start not from point 0, but a point closer to a similar problem. I won't get into this too much, but one of the examples in this is an idea called convolutional neural networks, where you're working with large images and you kind of convolute them. I think so, those who worked in digital signal processing, it's a way of combining two signals to get a third signal that is easier to work with. Okay? So convolution gets you this huge images, could be, each of them could be say 8 megapixel or something, right? Or 20 megapixel is very natural these days. And let's say you have a video coming in at 20 megapixels, now you've got say 64 frames, 64 times 20 megapixels, huge amount of data would work with. Okay? So instead of doing that each time, I mean, for that they would use say something called convolutional neural networks to reduce the problem size and then work with it. In that process, you can slip off some part of it and apply it to your problem, right? Which gets you to your output very much more quickly. So the Google ML API, some of them which I've used, like vision, there is what is that, speech to text, there is text to, there's video processing, there's translation. All of these, at some point, apart from doing core models, also use some amount of this transfer learning. And it's, of course, something that you can apply to your own projects also. The last thing that I will touch upon is the idea of, given that this is an automated system to find the model, can you automate that system itself, right? Can you make the system predict what is the model to use? So there's another area of work called reinforcement learning, where instead of you doing the work, you have two neural networks that kind of work with each other to say, do this, give me the result. If I find it, I don't know the final answer, but I know it's closer to the final answer. So if you've seen that game, AlphaGo, that won against the champion, AlphaGo, right? That's the game that's okay. So what it did was it played that game over and over and over again with itself until it became more and more competent. So neural architecture search is something like that, where instead of you trying all the combinations, because if you tried all the combinations, there's a huge combinatorial explosion, and you will not be able to get through your work, right? So instead, these two neural networks, they kind of work aggressively against each other to come to a particular model that works. So I'll take one last minute. AutoML, you might have seen the demo of this. Great tool, actually. If you had to train your own system sometimes, it will take you hours or days of training, whereas with AutoML, I was able to do it within a couple of minutes. About 10 minutes is what it took to do some kind of thing that I'll just show a quick slide show of. You need very big data sample sets to be able to work with that kind of training. With this, I just had to have about 10 images per type. Yeah? And there's a long time spent in tuning hyperparameters as a part of regular training. With AutoML, I didn't have to do any of that. Okay? And this is another thing that I demoed, and we are deploying it as part of somebody's, one of these startups' work by using AutoML. The whole process of training and evaluation to get, and also this thing called confusion matrix that says how good your model is, it's a part of that, and also allows you to create the model which you can then predict on. So what I did was I predicted, I put in a whole bunch of images, if you see here, that had like PAN card and all the just 10 images, like Schengen visa, some passport, and I come in and put some random PAN card that I found on the net, with not just a PAN card, but there's a hand in there, there's some kind of background, and it still is able to predict fairly well that this is a PAN card. Whereas with a very neat PAN card, it predicted with a probability of 1, that is 100%, that this is a PAN card. Right? And this whole thing I was able to get done with AutoML in about 10 minutes flat, which otherwise would have taken me probably weeks. And with, like I said, one company that I worked with, they were trying to do this for about a month. Right? And that I got done in 10 minutes, which is a solid improvement in time. I know I've spoken through this fairly fast. There's a lot of material. There's a last slide there. There's a bunch of certifications that I've done as part of Coursera. I would suggest that you try this if you want to do the ML learning and get into the internals of how it works. Okay? Deep Learning by Andrew Young is very good. The other two, the last one I have not completed because only 3 of the 5 courses are out. But the 3 that I've learned itself is great. All this transfer learning, then neural architecture search, all that I learned from that. There are a bunch of other courses with respect to the Google Cloud data engineer, Google Cloud architect, and associate engineer, which again is something that I've done myself, and I would recommend that you try it out. Yeah. With that, thank you. I know I've spoken fast, and I hope to, thank you very much. I hope to do more workshops, and maybe we'll get you hands-on training in working on some of the things that I've learned, at least to the extent that I've learned. And you can reach out to GDG or GCDC and they'll be organizing something. Yeah, thank you.